Hi guys, welcome to this video where we're going to have a look at the work for today. So you thought you got rid of me for a day, but here I am. So tough luck guys, I'm still going to be teaching you in a virtual way. A bit scary in that. Okay, so last period you might recall we were looking at some applications of differentiation. Now on the screen you should be able to see I've got OneNote open here, and there is some material on OneNote in the content library in the section on differentiation. Here are applications differentiation, which I'll be referring to and you can go back to and have a look. Now one of the things which is in your workbook on page 154 is a way that you can sort of structure the way in which you do these questions on the application of differentiation. So I'm just putting that in the middle of the screen at the moment. The steps we're going to have a look at in a video I'm going to show you soon will show you the sort of classic way that you do these kind of problems, where we're going to draw a diagram, have a look and see if we can find an expression for the quantity that we want to maximize or minimize. Often that will be, in terms of two variables, and then we're going to try and make that in terms of one variable so we can differentiate it. We're then going to differentiate, find out when that derivative equals 0, find the actual minimum or maximum quantity that we're after by using some substitution, and then just double checking that we've answered the question properly. Now the main part of the video that I'm going to show you is linked to here. This introductory part of it won't be there, but the rest of it is there. Okay, so yeah, we'll have a look now at this video on applications of differentiation, and then at the end of that I will explain what work I'd like you to try and do. Hi guys, welcome to this problem where we're going to have a look at an application of differentiation. So just to remind you guys, you should also be looking at the OneNote. So I'll just drop out of this here and bring back the OneNote. So this material here on OneNote, so you've got different brief notes here, but make sure that you are reading those as well, and also looking at the video, and the link to the video will be up here later. Okay, so let's just get that out of the way. Okay, so in this problem where we're going to be looking at application of differentiation, usually what we're asked to do is from the description find out something about either maximizing or minimizing. So some examples of maximizing could be something as simple as, okay, what's the maximum profit in a given situation? Or an example of minimizing, minimizing, yeah, that's right, okay, is something like in this situation, which could be cost. So that's the kind of context, not always, but quite often. Or another minimizing thing, we could be making some packaging, so we might want to minimize the volume, or we might actually want to maximize the volume, or we could be trying to maximize the surface area of something. Okay, so in just about all these kind of situations here, given a written description, and I'm taking question 346 here, so I'll just read out what it says, and you can also have a look at that in your workbook. It says a farmer needs to have a water storage container in order to fight forest fires. Now the water storage container has an open top, so here's our open top storage container, a rough diagram of that, and it has to have, or is to have, a volume of 20,000 litres. The length, we're told, of its base is twice the width. Now if you look at your workbook, they've actually given some labels here to help you. If they didn't, we'd have to do that ourselves. So we might call this the width here, and so the length is twice the width, so that will be 2W, and the container has a certain height. So putting variables onto your container is an essential, and we are talking about volume here. So one thing we can immediately say is, well, hey, maybe I'm going to need to do something with the fact that the volume of our container is going to be the length times the width times the height for a cuboid, which simplifies to 2W squared H in this case. And we actually know what the volume is. It's 20,000 litres. Now notice these units though, these are in meters squared. Okay, something about the cost of the area of the sides and the base. But this is in litres. Well, meters and litres, or meters, well, they're just not compatible units. They're different units. So what we are also told, if we weren't, we would have to do this conversion, is that 20,000 litres is equal to 20 meters cubed. So I'm going to work things in using the unit of meters, and area of course in meters squared and volume meters cubed, but they're compatible units. So I'm going to put 20 here, and you might notice that that simplifies to 10 equals W squared H. Right, that's just taking the information that we're given and something about the volume here. Now, what else are we told? We're told the base is going to cost $75 per meter squared to make. So where's the base? Well, I'm just going to try and draw that in roughly here. So this is the base down here, the floor of our tank, and we're also told something about the sides, that they cost $40 to make. So this is a big clue about what's going to come next. They say find the cost of materials for the cheapest container. So we want to get the cheapest container. So that means we want to minimize the cost. So I need to get an expression for the cost of making this container, and the cost is going to depend on the area of each of the sides, or the sum of those. And then to find the minimum costs, we're going to have to differentiate that cost equation to find out when it's a minimum. Okay, let's go for it. Okay, to get the cost equation, I'm going to get the area of all the different sides. Remember, it doesn't have a top. Add those together as much as possible, but also realize that it's a different cost for the sides and a different cost for the base. So let's try and come up with our cost equation. So I'm going to call C cost. Right, let's have a look at the base for a start. Well, the area of the base would be 2W times W, but the cost would be 75 times that, because 2W times W is an area in meters squared, and for each meter squared area it's $75. So I think it would be reasonable to say the cost of the base is going to be 2W squared, its area, times 2, which of course can be simplified soon. Okay, the next bit, let's go on and add now the sides. Okay, well the sides, notice, have two different dimensions. Okay, if we take the front here, it's 2W times H, and we have two of those. Okay, so we've got 2WH times 2, and that's going to give an area of the front and the back, and that is going to be times 40, because it's $40 for each of those square meters. Okay, so that's the front and the back, and let's add on the two sides. Okay, so this side over here, okay, the right side, is W times H, and we also have a left side. Okay, so that's going to be another, so that's two lots of WH, and each of those square meters times 40. Alright, let's try and simplify this. Alright, this is going to be 150 W 2W squared. So 150 W squared after multiplying by 75, of course. Okay, that's going to be 4WH times 1 times 40. 4 times 40 is 160. So that's going to be 160 WH. And this is going to be another 80 WH. Right, so we can simplify further. 150 W squared plus 240 if you add the WH terms together. Okay, now this is an expression for the costs. Now if you have a look at the material on the OneNote, it mentions there that we can use this mnemonic, Dell's det, to try and, my mouse pointer's gone, let me just try and get it back here, here we go. Alright, so Dell's det, well that talks about, just get this working again, 1 second. Yep. Alright, so diagram, well we've done that. Okay, it says express the problem that needs to be maximized or minimized, often in terms of two variables as an equation. Well, we've just finished that. This is this equation here. Now, the next part is to link the variables here with something. Why? Because I need to differentiate the cost to find the minimum cost. Because minimum or maximum is when the derivative equals 0. So I can't derive at the moment, and I don't want to use implicit differentiation because that wouldn't really be useful here. But this is where this other piece of information is useful. So I'm going to link the W and the H together, which I've already done here. And now I'm going to try and replace H in terms of W. Why H? Because it's a lot easier to make H the subject of this. So if I do, I get H is equal to 10 over W squared, and let's put that into this equation to make it in terms of one variable which we can then derive. Okay, so 2. Okay, and yep, bit of simplifying we can do. 2,400, 240 times 10. We have a common factor here, so we can cancel that. So I'm going to get 2,400 over W, which I might write as W to the power of -1, because it makes it easier to derive. Okay, so one equation for cost in terms of one variable. Great. So now we can derive with respect to W. Right, so this is a power situation, so 300 W. That's again power situation here, so minus 2,400 W to the power of -2. And I'm just going to write that as a fraction, this part, W squared on the bottom. Okay, so having derived for maximum and minimum, so for the minimum cost in this case, we have to find out when that derivative is going to equal 0. Okay, so that means this equal to 0. Simplest way of doing that is actually move this negative term to this side and then cross multiply. Yeah, you could put it over a common denominator and all that lovely stuff, but this is simpler. Okay, and if you cross multiply here, you get 300 W cubed equals 2,400, and if you divide both sides by 300, you end up with a very nice little equation. W cubed equals 8, and therefore W equals 2. Okay, and yeah, I suppose we should really show that this does give a minimum, okay, which would mean we have to derive this again This one here, probably the easier form to do. Yeah, I suppose we really should do that. So let's actually get our second derivative. Sometimes in the NCA exam, they say something like, you can assume that the second derivative, now for a minimum, we want second derivative to be greater than 0. So they'll say, you can assume that the second derivative is greater than 0. Well, they haven't told us that here, so we're going to have to do it. Right, so let's take this, and here we go, derive again. So 300 plus 4,800 w to the power of -3. And if you just put that maybe in this form, it might make it clearer that you're going to have a positive term here and another positive term here. Well, if x is equal to 2, the second derivative will definitely be greater than 0. Therefore, we have a minimum. Minimum what? Minimum cost when w equals 2. Alright, so we're almost finished. The question was, find the cost of the cheapest container. So let's go to our cost equation. Okay, and what else did it say? Find the cost of the materials. Yeah, it doesn't actually ask for the dimensions, although in the back of the book they do give h as well. I'm not sure why. We could actually just put that 2 into our cost equation here. So I'm going to do that. So the cost will be 150 times 2 squared plus 2,400. I'll put that over w now, easier to use, and w is 2. So that was a square. Okay, so that's 4 times 150. Okay, what's 4 lots of 150? 600, I think. 400, 4 lots of 50, 200, yep, 600. Plus that halved is 1,200. So I reckon that's going to be a total of $1,800 for the minimum cost. Okay, so there's an example, one example of an application of differentiation. Now, we'll, at the beginning of tomorrow's period or the next period, we'll definitely just get you guys to go straight into trying another question, perhaps in some groups. See if you can try and replicate this kind of working. But coming back to our deals debt, okay, so this was the substitution stage here where we put it in terms of one variable. We then differentiated and we equated it to 0. Okay, here. And then back substitute into the original problem to find the maximum minimum. Yep, that's what we did here. So that was the B part. And test your answer by rereading the question. It could be the problem wants both variables. Well, in fact, this problem doesn't, although the back of the book does give both W and H. Yeah, it just says find the cost of material, so we've done that. Okay guys, so we've had a look then at an example of this applications of differentiation work, and what I'd like you to do now, if you think you need to have a look at another example, then there are two examples, one on page 155 and another one on page 156. Now don't spend your whole period just reading over examples. You actually got to try some questions. So maybe if you really think you need to, have a look at one of those two examples and then go on to the questions on page 157 through to page 160. The questions on page 160 are excellence questions, so you know they're not easy, and the ones back on those other pages are merit level ones. So have a go at that, and for homework over this period and to complete it by Monday, I want you to have a go at the questions up to the ones on page 300 159. That's up to question 353. For those of you who think you're a pretty good student, pretty good at this stuff, have a go at the questions on page 160 as well. Question 355 is a real doozy, so that might challenge you. Okay, so guys, have a good day, and we'll catch you next Monday. The relieving teacher today should also be giving you a hard copy of revision assignment number 4. So remember, that is due next week, Wednesday. So nothing like keeping you busy, eh guys? Have a good day. Catch you, gentlemen.